Okay, well, I'm assuming that more folks will be making their way in here. I think I'm gonna go ahead and get started, guys. Welcome back. I hope you had a nice spring break. Maybe got a chance to rest up a little bit and enjoy some nice springtime weather. I think it's been pretty nice lately. So I hope that you had a good break. Got at least do a little bit of some fun things and a break from the routine of coming to campus every day and everything. So that's kind of nice. Let's see, so we're kind of back on track here. Just a couple of announcements before we dive back in and kind of recap what we were doing before. First of all, don't forget there is a homework assignment due tonight. I do have my full contingent of office hours later today, 2 sessions, one of them right after my second class at 8 o'clock. And then I'll take a break at about 9 o'clock, and then I'll be back at about 10 o'clock. And you can have the rest of the evening to finish up that assignment. I think 2 people have already turned it in. So just looking for the rest of you to get that into me by tonight. Mostly, some of the ring theory homework. For the most part, it's relatively standard problems and so on, but there might be a few details that you want to check with me, or just if you're feeling shaky about any of it, definitely let me know. So that's due tonight, work number 11. The next assignment, I have posted that now. That one will be due next Monday. And included in that one, I keep talking about these videos that I want you to watch with these 2 results. And I keep forgetting to send them out by the time I get down to my office at 8 o'clock. So I decided to just put it into the next homework assignment. So homework number 12 will start off with whenever you've got about 20 minutes. I think each video might be about 11 minutes long. I'd like you to watch and take notes on these 2 major results about ideals in the polynomial ring over a field. F of x, this is a really well-structured example of a ring, and we understand its ideals very, very well. So in particular, every ideal of f of x is always principal, and precisely when the principal ideal, when the generator of the ideal is irreducible over the field, that's when you get a maximal ideal. So both of those results are in videos. I recorded them. I watched myself again make the video last year. It looks like I'm not looking right at the screen. I don't know what happened with the camera in the room at the time. But anyway, I think my voice is really clear. It's on the glass board that I've been using religiously now to make new videos. So take a look at that. Let me know what you think. Give it a like if you like it. And that'll be just part of the homework number 12. There's of course some other problems to do from chapter 6 still, as well as some of the more recent stuff that we just kind of finished up with before the break. So that's one announcement. The other announcement is that I posted over this past weekend a resources folder for our second midterm. Let me just say a quick word about that. So our second midterm, we only have 2 midterms before we get to the final. So midterm 2 is going to be on Wednesday, April 24th. So we have homeworks due tonight. There'll be another one due next Monday, and then there'll be another one after that still. So 3 more homeworks actually, including tonight's, before we get to this midterm, which is 2 weeks from Wednesday. I put together a resources folder. It has a sample, basically the exam I gave the last time I taught the class is in there for you to practice on. There's also a review packet with a whole sort of glossary of important terms and kind of what types of things should you be able to do for this exam. And then I have a handout with review session problems on it. So I am planning to go through those in review format, but that review will be let me take that back. That review will be partially outside of class time. So one of the little slight hiccups with this midterm is that unfortunately I actually have to be out of town the weekend before this exam. So I will not be around. I will try to have Zoom office hours, but I will be actually out of state. So I'm gone. When am I leaving? April 18th through 21st. I will be gone all 4 of those days. So what I have decided to do is hold an early review before I leave. So that's already next week on Tuesday. We're actually in good shape with the material for the most part. So I think the 16th is that right? Yeah, that's next week on Tuesday. The day after all of our taxes are done, we'll be able to relax and chill out and just have a review session. And so I'll do one, remember last time I did 2 review sessions, so I'll do the first one on that Tuesday. I think I picked sometime in the afternoon. I can't remember exactly what time I picked. Might have been, I tried to pick some time I thought would be okay, like maybe 2 o'clock or something. And then you don't have to come. I'm gonna record it. I'll send out a link if you're not able to make it, no worries. And then I'm actually gonna do the second review in our class on Monday, April 22nd. We are in good enough shape with the material that I think I can actually do that. So we won't have any new material that day, which is literally just 2 days before the midterm. We'll just do some additional review. I think that's fine. So that's my plan for the review sessions. And I will try to have some office hours here. And certainly when I come back, I'll be back by the morning of the 22nd. I'll have some extra office hours on the 23rd and certainly on the 24th before 4 o'clock, I'll be around as well. So there'll be, I think it'll still work out okay. But I just have to be a little bit ahead of schedule on all of this stuff to make sure about that. So what's it going to cover? It's all in the review packet, but it's going to go all the way back to the stuff about group theory, where we talked about conjugacy classes, the class equation, the index theorem, proving that groups of certain sizes can't be simple, things like that. And then moving into the ring theory, ideals, the stuff in chapter 6 that we just finished before spring break. And now we're actually jumping into chapter 11. I think I might have at one point said it was chapter 10. And in fact, on one of my handouts, it says chapter 10. That's because it was lined up with an old version of the book. So we're actually moving to chapter 11 in the material we're going to start on this week. So I don't mean to confuse everybody with all this jumping around chapter 9, then chapter 3, then chapter 6, then chapter 11. What kind of an order is that? But that's kind of where we're at. So that is about the size of it. That's what I've got to say about all that stuff. Does anybody have any questions for the moment on that? Yeah, so just when you have a chance, take a look at the midterm 2 resources folder. I've got that in there. I hadn't decided yet about whether we should have a quiz or not. There's enough homework that I'm not sure. I think we'll have a quiz, maybe on the 17th or something. We'll either have a quiz or I'll give you a mock quiz to just take for yourself to just go look at on your own. One way or the other, I'll do something like that as well. So I'll let you know soon. I just need to double check my time frame. But okay. So anyway, that is just my quick little recap to get everybody oriented as to where we're at. Does everybody have this handout? Did everybody get this that I just passed out? Oh, okay. So just gonna quickly review a couple of things. Remember this big theorem about creating fields by modding out by maximal ideals. Theorem 6.15, right? An ideal is maximal in a commutative ring with 1 if and only if R mod M is a field. But at least in the case when the ring R is f of x, we know when the ideals are maximal, right? Precisely when the polynomial that is generating that principal ideal is irreducible over that field. Great, so we know how to create fields very easily. All we have to do, if we want to do it over polynomial rings, is just find some irreducible polynomial over the field and mod out by that. So we did that, of course, before the break in this example. So a great example here is, just put it here, is we take R to be Z7 of X, right? So that's exactly this context of f of x here, right? Z7 is a field. We build polynomials over that field. And then what we did is we built the maximal ideal, which is the principal ideal generated by x cubed plus x squared plus 1. This polynomial, this is my p of x, right? It is irreducible over Z7. Why do I know that so quickly? Can somebody remind me again? Why is this polynomial irreducible over Z7? I'm sorry, not Z7. This should be Z2. That's my mistake. I'm getting ahead of myself. over Z2, Z2 of X, that's what I meant to write. How do I know that this polynomial is irreducible? How do I know that, yeah, that this is irreducible over Z2? Yes.
You could try one. Like that.
You can try what values?
Oh, one.
-1 is the same as 1 in Z2.
Oh, yeah, just one.
1, and what's the other number we need to try? 0. Okay, this Z2 has two numbers, which are 0 and 1. If you try either one of them into the polynomial to test for whether they are roots, they will not be, right? If I plug in 0 for X, I don't get 0. If I plug in 1 for X, I don't get 0. So you plug both of those values in. So this has no roots. And remember that if a polynomial has degree 3 or less, the only way it could be reducible is if it had roots. This one does not have any roots, which means it's irreducible over Z2. Therefore, if I form R mod M, this is a field. Right, and the size of the field, by the way, is always, in the case of these finite fields that we're constructing, 2 to the 3rd power. And the 8 elements of the field are on this handout, and I actually have, it's a two-sided deal. One side has the addition table in it. This is how you do addition. Literally, you're adding polynomials mod 2. And on the other side, I wrote out the multiplication table, right? So I did the same thing on the back side. The back side's a little bit harder because remember, when you do multiplication of polynomials, the degree of the polynomial might creep up to something greater than, you know, just a perfect square. See, the elements of R mod M have the form ax squared plus bx plus c, right? Anything involving x cubed or x to the 4th or anything higher than that can always be cut back down to something of this form. And that's because x in the world of R mod M, x cubed plus x squared plus 1 gets identified with 0. Yeah, so that means x cubed is literally replaceable with x squared plus 1. So technically, every element of R mod M is expressible in this form, which is why there's 8 elements in this field, right? I have 2 choices for A, 2 choices for B, and 2 choices for C, either 0 or 1 for each of those coefficients, right? So that gives me 8 choices. It's a field of size 8, essentially, but the multiplication table takes a little bit more time to write it out. If you have this table in front of you, well, then of course you can really verify it directly from the table that it's a field. Because you'll notice that everybody has a multiplicative inverse. Every single row and column, other than the 0 row. Obviously 0 does not have an inverse, it doesn't have to have an inverse. But if you look at any other row or column, you'll see that everybody has an inverse. So for example, you'll see that if I take x and I multiply it by x squared plus x, right? If you believe the table, that's equal to 1. So if everybody can follow that on their little table, right? You go to the x row, the x squared plus x column equals 1. That would be calculated by multiplying this out and using this relation to reduce x cubed back down to lower powers of x again. So these two guys are inverses of each other. And you can just check that for everybody. Everybody other than 0 is going to have an inverse that you can literally read off from this table. Okay, but if you don't have the table in front of you, then it's not quite so easy, right? I mean, then we have perhaps slightly harder problem in front of us. So I would like to just make sure everybody knows how to do this. We probably have seen this before, but 407 is always a little tricky because it depends on whose version of 302 you saw. So let's try this warm-up problem just to kind of get the wheels turning again today. Suppose we take Z7 of X, which is what I was getting mixed up with over here, and I'm going to mod out by the principal ideal generated by x cubed plus 3x squared plus 4x plus 1. I'm first going to ask whether that's a field. I would like to point out that even if the answer is no, the second question still can make sense, because even if something's not a field, some of its elements might still have multiplicative inverses. So it's okay to ask a question like number 2, even not knowing for sure that we have a field. So let's talk about whether we have a field here first. How am I going to decide whether this is a field? Larry,
If it's a field, then by, that idea, the first one.
yes,
No, the theorem. That
Yes.
implies that its ideal has to be maximum.
okay, this would need to be a maximal ideal, and how am I gonna decide that? Whether or not it's irreducible over Z7. And because it's only a cubic equation, irreducibility is equivalent to no roots, right? So it literally is a matter of, so I'll start solving it over here. It's literally a matter of just figuring out whether there are any roots of this polynomial in Z7. Since it's a relatively small field, that is a brute force calculation. So for the solution to the first part, right, so we could just set P of X equal to the polynomial here, x cubed plus 3x squared plus 4x plus 1, and just start testing for roots. So I'll kick the ball off here, but I won't probably go through everything. Right, you check P of 0, you get 1. That's not a root, okay? You check P of 1. 1 plus 3 plus 4 plus 1 is 9. Which now remember, you just always have to remember which base field you're working over, Z7. So in Z7, that's the same as 2, but regardless, it's not 0. So as long as none of these things comes out to be a multiple of 7, then you don't have a root. So you try 2 and you get, what do we get here? 8 plus 12 is 20. It looks like 29 this time. All right, well, 29 is also not 0. I will leave it to you guys to check all of these. I will point out that when you get kind of most of the way done, let's suppose dot, 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 2 things missing. By the time I get to P of 5, I would actually recommend that instead you go ahead and work with -2. It's just easier. So then I have -2 cubed, which is actually -8. Plus 12 minus 8 plus 1, right? So you can just go ahead and plug in -2. And I think that comes out to -3, and that's not 0 again, right? And P of 6, so just a little trick that when you don't have a calculator in front of you, that you can literally just change these into negatives. P of 6 would just be P of -1. And if we put in -1, we are going to get, well, I think -1, which is not 0. So you can just check that there are no roots. So P of X has no roots in Z7. Thus, since it's of degree 3, P of X is irreducible. It is irreducible over Z7, meaning that R is a field by the results on the board over there at the left. So we do have a field here. This is a yes. Okay. So that means that every non-zero element, by the way, what's the size of this field? Just to give you a hint, if you need to, look back over here. This was a field of size 8. Right? Because everything was expressible as ax squared plus bx plus c, where a was either 0 or 1, b was either 0 or 1, and c was either 0 or 1. My question is over here, what is going to be the size of this field? 7 cubed. Just 7 cubed, right? Same thing. Because the highest power of x here is x cubed, I can use this polynomial as a relation to reduce anything of the power x cubed or higher down in terms of lower powers of x, meaning squareds, linear terms, and constant terms. So essentially, this is 7 cubed, right? And the elements, I'll just add that here, the elements of R have the form. Okay, I'll just put it in brackets. It's literally the same as the story over there on the left side. Ax squared plus bx plus c. The only difference here is that a, b, and c now have up to 7 different choices because the scalars are coming from Z7 now. Right, so I'm putting brackets around my elements to just reminding you again that that is a notation that is suggestive that we are working in the quotient ring, or in this case, field. Right, so these are this is technically a coset. This is technically a coset here. So when I'm writing brackets, like on problem 2 here, I'm putting brackets, that's actually on purpose, right? To emphasize, we're talking about an element of the quotient structure. Question?
You said that regardless of the size of our quotient group, they all elements can be expressed as that ax squared bx.
Yes.
Okay, so it's not, you wouldn't say it's ax cubed plus bx squared plus x.
No, because, okay, so the thing is that what we know here is, let's just make sure we're all clear about this, that basically this thing here is being set equal to 0 in the quotient ring.
Right.
And brackets respect addition and multiplication, because that's how the multiplication and addition work in the quotient ring. So I can solve for, bracket of x cubed in terms of these guys. So anytime I see an x cubed, I'm always going to be able to re-express it using lower powers of x. And by re-express it, I mean literally this is equal to this in the quotient ring. So it's a totally fair statement to say that every element is expressible in this form right here. Yeah, good point. Is everybody else okay with so far so good on this? Okay, so we have a field, which actually means that every element has a multiplicative inverse. That's sort of the definition of a field. And in particular, I'd like to find one here. Now, I'm obviously not going to do the multiplication table. This is what, 343 elements. So it's definitely going to be too much to have a table like this written out for this field. So instead of that, now we've got to sort of figure out specifically for this element, what is its inverse? Does anybody know how to figure that out? I know I'm kind of starting off on the computational side today rather than the theoretical side, but I just want to make absolutely sure. Yes.
It would be that's coset multiplied by something of the form ax squared plus bx plus c equals 1.
Okay, I could solve it that way. I could say, well, let's take this thing and set it into an equation where it's being multiplied by whatever its inverse is going to be, which we don't currently know. So we could write it as ax squared plus bx plus c, set it equal to 1, and then start calculating out on the left-hand side, and we'd have these unknowns a, b, and c that we try to solve for in a system of equations of some kind. That is totally a reasonable approach, but it's not quite as sort of direct as maybe another way of doing it. Does anybody know of another way of doing it? So maybe if we're not sure, before we do part 2, I'm going to propose a different question to you and see if you know how to do this question. This next question should be more familiar. What if I asked you, what is the multiplicative inverse of the number 77, and I'm viewing that as a coset, in the ring, and this ring, by the way, is not a field, but that's okay, it's a Z122. So Z122 is not a field because 122 isn't prime. In fact, so this will have 0 divisors. For example, 2 times 61 would be equal to 0 in this Z122. So it has 0 divisors. So it's not even an integral domain. Okay. But there are still units in that ring, right? This is still a unit in the ring, precisely because it is relatively prime to 122. So obviously the equation that we are interested in here would be something like this: 77 times x congruent to 1 in mod 122. If I could solve this for x, I would know what the inverse of 77 is. So how do we do that? Does that look familiar? Anybody been in number theory class lately?
Is it the Euclidean algorithm?
Yeah, we just use the Euclidean algorithm, right? So we start with 122. Ooh, green. 122. Can you guys see this color? Okay, 122, we divide it into 77, right? It goes one time. Divided into 77, and we look at what the remainder would be, which I guess would be what, 45? Okay. Then we take the 77 and we divide 45 into that. So we would take one factor of 45 goes into that, and we have another remainder. This time the remainder is 32. Now we do it again. We put 45 on this side. Now this should be looking familiar. Has anybody done this before? Please tell me, at least in 302, they would have to do this. Certainly in 430, they have to do this also. 32 plus 30. Have they done this in your class, Larry?
Euclidean algorithm?
Yeah.
Yes.
Okay, good. Just making sure. So we have that. Then we take 32 and we divide 13 into that. That goes 2 times with a remainder of 6. Then we move 13 over here and we divide 6 into 13. It goes 2 times with a remainder of 1. The last non-zero remainder is the greatest common divisor of 77 and 122. But if I actually want to get the inverse of 77, I now have to run this backwards. This is the, as Jaden pointed out, this is called the Euclidean algorithm. This is like super standard material, very important material in the world of algebra. But we have to actually run it backwards in order to find the inverse of 77. So what do I mean by run it backwards? Let's just do it here. I'm doing this fairly quickly, guys, because I think this should be pretty familiar. And if it's not, you certainly can come talk to me about it in more detail. But essentially, you start at the bottom and you write everything in reverse. So 1, you solve for 1, it's 13 minus 2 times 6. The only thing here is you have to be a little bit systematic about how you're doing these steps in reverse. So you could see, for example, that, oh, I can rewrite 13 in terms of 45 and 32, but don't do that yet. Because I first want to write 6 in terms of 32 and 13. And if I replace 13 in terms of 45 and 32, I'm just going to have to do it again in the next step. Better thing to do is leave the 13 alone and just replace the 6. So the 6 is 32 minus 2 times 13. It'll look something like that. And then before I go any further, I would clean this up, because I have 13s appearing in 2 places. So this should be 5 factors of 13 minus 2 factors of 32. At any given point, you can always stop and make sure that it should still equal 1. Otherwise, there's a calculation error here. Okay, so then I've got 13 and 32. These are the 2 hot numbers at the moment, but I always go with the smaller one first. So I take 13 and I'm going to rewrite it as, what is it? 45 minus 32. So 45 minus 32. Are we taking bets on whether I'm going to run out of room over here yet? Certainly looks like I might. Anyway, I'm going to try. So this needs to also be cleaned up a little bit. Let me just come back over here. I need more. I'm not even going to try to get that in there. You guys can keep working on it while I'm erasing, because I think you probably know what I'm doing here. So this is good thing to review. It's definitely something you want to be able to do. I'm going to clean that up before I go any further. So what do I have over there? I have 5 factors of 45. And then it's what? Minus 7 factors of 32? Minus 7 factors of 32. Great. So we would have that one. And then I'm going to take 32 and replace that. This is 5 factors of 45 minus 7 factors of the smaller of the 2 numbers, which is 32. I rewrite that as 77 minus 45. Yay, I see the 77 now showing up. Let's clean that up over here on the side. It's actually going to give me 12 factors of 45 minus 7 factors of 77. Okay, and then finally, I take the 45 And I rewrite that one as 122 minus 77. Yeah, minus 7 factors of 77. I'm gonna clean that up one more time. So this is 12 times 122 minus 19 factors of 77. And I think that should be correct. Did this here? Yeah, okay, great. So just in conclusion, what we have is that 1 is equal to 12 times 122 minus 19 times 77. And that equation is true in the integers, so of course it's true in any congruence world Z mod n. So in this case, Z mod 72. So I can put brackets around everything here. And when I write those brackets, I'm referring, of course, to Z122 congruence classes, right? So far, so good. And the thing is that in Z122, this part is 0. Right? And so whatever 77 is multiplied by is its inverse. So the inverse of 77 is negative 19. And of course, if you don't like negative 19 is fine with me. If you don't like negative numbers, you can just add 122 to that and report an answer that's actually a positive value, like 103. Okay, so you're not going to just stumble on that by accident. You actually have to do the Euclidean algorithm forwards and backwards in order to figure out the inverse of an element in that ring. Okay. So with that in mind, is everybody okay with that? Any questions? It's just like a quick review of what I think probably is pretty familiar. I now want to tackle this second problem here and just show you that it basically is the same thing, right? The way you do this problem here, it's the same thing, it's just a little bit messier. Okay, so now let's do the solution to question 2. So I want to find the inverse of 2x squared plus 3 in the ring R. So what did I do over here? I started with 122, which was what I had modded out by essentially. So in this case, what I'm modding out by would be x cubed plus 3x squared plus 4x plus 1. And what I want to do is I want to divide it by 2x squared plus 3. And I'm going to get some quotient and some remainder here. I'm going to leave some space here. What we might need to do, guys, is get a little bit of scratch paper going. If you have a margin in your notepad there that you could possibly write this on, it might be a good idea, right? So what I like to do, I just write down x cubed. This is scratch over here. This is just my scratch calculation. So if I take, now has anybody seen this before? This might be new. We're basically doing the same Euclidean algorithm, but now I'm doing it in f of x. Has that ever shown up in any? I'm just always curious. Have they done that for you in 302? 303. Okay, so maybe even with polynomials they've done it. Okay, so I'll do it fairly quickly, but we're just going to divide this into 2x squared plus 3. Okay. So this is my scratch right here. So I'm kind of just doing long division, right? And so I have an x squared here, but I need to get x cubed, so I put x up here. But there's another problem, which is that I shouldn't have a 2. So if I take 2x squared and multiply it by x, I get 2x cubed. But I only want to get x cubed in order to be equivalent to x cubed here. So what do I need to put in front of that x? One more time? 4, exactly. And that's because 2 times 4 is 1 in this space ring, right? So the inverse for 2 is 4. So we definitely get 4x there. Now what I do is I just take this times this, right? I'm going to get 8x cubed, which is really just x cubed, plus 12x. Just write it like that. And then I'm going to subtract. When I subtract, I get 3x squared minus 8x, but that's really minus x and then plus 1. So 4 minus 12 is negative 8, but negative 8 is the same as negative 1. And now I need somebody to help me out with what this constant needs to be here. So 2x squared is going into 3x squared. 2 times what is equal to 3 in Z7? Yeah,
It's not negative. squared. Oh, never mind, because you're subtracting.
taking this line minus this line. Yeah, no, that's all good. It's all good. I gotta solve this little equation. 5, just do it by in your head. Yeah, just it's definitely 5. So I'm gonna put 4x plus 5 there. So that gives me 10x squared, which is the same as 3x squared plus 15, but 15 is the same as 1. So now I subtract again and I just get negative x. Now this is my remainder this time, right? I can't do anything better than that. This is like having a number that's less than 122. I can't divide anything else into it here. So we have our quotient right here, my friends, and our remainder is right here. So we put it over here, 4x plus 5 and a remainder of negative x. Okay. By the way, in Zn, there is no big deal about negatives and positives, right? Because after all, you could take any negative expression and rewrite it as a positive one, or any positive expression and rewrite it as a negative one. So it really doesn't matter. Okay, so that's great. Now what I have to do is move the 2x squared plus 3 over here, and I need to divide it by whatever the previous remainder was, which was negative x. And I'm gonna get a new quotient and a new remainder. That means I need new scratch paper. Okay, so let's just do it over here. So I'm gonna take 2x squared plus 3. I'm gonna divide it now by negative x. And this is not too bad, doesn't look too bad anyway. I'm gonna have to put a 2 and a negative 2 and an x up on top to make this match out. And so that gives me 2x squared. Subtract down and I just get 3. That's all there is to that. Right, so my quotient is negative 2x and my remainder here, whoops, I kind of wrote that wrong. This should be plus whatever the remainder is 3. Okay, pretty straightforward. And now I do it again. I have to move the, well, actually, I'm basically done. The 3 is my remainder. Technically, we need to get a 1 there, but I can get a 1 by just using the fact that 3 is already multiplicatively invertible in Z7. So I can just find, once I get to any constant here, I'm essentially done. As soon as my remainder is a unit, I can just express it in terms of 1 by finding its inverse. Okay, so this is all happening. I'm using these equal signs a little bit loosely because of course these really are in the congruence world of the ring R over here as we're doing it. So just keep that in mind as well. So now I'm going to run it backwards again. Going to run this thing backwards. Run backwards. That was the Euclidean algorithm for polynomials. Now I'm doing it backwards. So I start with 1. You always have to start with 1. And again, I'm being a little bit, I'm just assuming that we're working in congruence land here. So I'm going to write this as 1 equals 5 times 3. Then I'm going to replace the 3, which was the previous remainder, with 2x squared plus 3 minus, I'm going to cancel those 2 negatives and just write it. Well, actually, I probably shouldn't do that. I'm going to write it. I want to get a negative x into it. So minus negative 2x and negative x. So I will just leave it exactly as I found it, which would be like that. And so this is equal to 5 times the quantity 2x squared plus 3. Let me get my camera over here. It's a little bit easier for these people to see. Minus negative 2x times, now I have to rewrite negative x here as x cubed plus 3x squared plus 4x plus 1 minus 4x plus 5 times 2x squared plus 3. So it's a little bit messy. This is what we have to keep track of. Okay. So anything involving, I'm gonna start simplifying this now. Anything involving x cubed plus 3x squared plus 4x plus 1 is really just going to be 0. In the quotient ring, it gets canceled down to 0. So the question is really just, so how many multiples of 2x squared plus 3 are there? So I'm going to factor out 2x squared plus 3 from everywhere that I can see it and see what I get. I've got a 5 right here. Okay, 5 right there, and then here I have, this is really a plus 2x. This is 2x times 4x plus 5, right? And it's with a minus on the 4x plus 5 part, so negative. Actually, this becomes a negative. It's like a triple negative, actually. 4x plus 5, like that. Okay. We following that? Sorry. So whatever this thing is in these brackets is the inverse that we're looking for 2x squared plus 3. You guys with me? Yeah. Let me just work on the brackets real quick here. This is a 5, and then minus 2x times 4x is 8x squared. Oh, but 8x squared is just x squared. Remember, 8 is the same as 1. So I'll just replace it with x squared. And then I also have a minus 10x, which is really minus 3x. 10 is the same as 3. You could sit right up here, my friend.
I know, but.
Then you wouldn't have any trouble at all unless you're cheating off Victoria. Okay, so let me just make sure, is that what I ended up with here? Why is that not what I have? Oh, I know what I did wrong. Does anybody else know what I did wrong? I made a mistake. You have to forgive me, it's a Monday. This 5 right here needs to be distributed through everything. So I forgot to do that. I put the 5 here, right, with the first part, but this 2x really should have been a 10x because it's 5 times 2 here. So that should have been 10, but of course 10 is really the same as 3. So everybody follow that? Here's a 2 and a 5. That 5 needed to get distributed into that expression. So I'm putting 5 times 2 together, which is actually 10. And 10 is the same as 3. So let's try this part again. Now I'm going to get 5 minus 12x squared. Let's see, 12x squared is the same as 5x squared. And then minus 15x. 15 is the same as 1 in Z7. Now, does that look any better? That does look much better. So that is, I think I have it correct. I just forgot to distribute the 5. Been hanging out with my 250B students too long. Don't tell them I said that. Okay, so what does this tell me then? This tells me that the inverse of 2x squared plus 3 would be, I'm going to write that as 2x squared. So negative 5 can be rewritten as positive 2. And then I'll leave the minus x and then plus 5. That's fine. So that would be a perfectly good answer. If I ask you to do this on an exam, of course, you will have no trouble with it, but you'll also want to maybe check your answer. So if I multiply these two things together, I should get 1. If I multiply them together, I'm going to have some work to do. Because if I were to sort of check that these are inverses of each other by multiplying them together, I would come across things like x to the 4th right here. So I'd have to figure out, what is x to the 4th? Well, I can reduce it using this relation right here that allows me to at least replace x cubed with something smaller. And then eventually I could replace x to the 4th with something of the form ax squared plus bx plus c. So it would take a little bit of work, but you could verify that that really is the inverse of that element. So what do you guys think? Are we feeling okay? This is finding inverses of elements in finite fields. It's very computational, which I know is, some people love that, some people hate that.
Try to give you a little bit of everything around here. Questions at all?
Could it be negative 3x squared, or do I have to?
Up here, this?
Yeah.
That is a minus, can't you see it?
Oh, yeah. Not the imaginary.
I accidentally partially erased it, yeah. Okay, there we go. Is that good for everybody else? Everybody good? Okay, sweet. Okay, so I think I'll leave it at that. This is just kind of a warm up. It's been 12 days since we had class. Sometimes I feel like, oh, come back from spring break. It's like the hardest class to ever get through, because it's like we've got to get the wheels turning again. So I thought we'd start with something a little more concrete and practice through it. So if there's no more questions on that, I really am now ready to sort of move into the field extension theory, which I had started on the very end of class last week on Wednesday before we took our break, and then I just kind of punted on it because we were running out of time, and I'll just start over after spring break. So we are now going to jump to chapter 11. So new section here, and this is all about field extensions. So field extensions, this is what we're going to talk about, and the theme of this chapter, right, guys, is basically going to be that we are going to study relationships, right? We're going to study relationships between fields that are contained inside of other fields. So it's relationships between fields. This is the theory of field extensions, chapter 11. So we can, of course, give nice examples of this right off the top of our head, because we know lots of examples of fields already. First example, we might start with the rational numbers. That's a field. It's a field that is contained inside of another field, such as Q of radical 2, Q adjoin radical 2. That in turn is contained inside of the real numbers. That in turn is contained inside of the complex numbers. So we can talk about relationships between these fields that are contained one within the next, right? Or another example that's more along the lines of what we were just practicing is we can really take any field, F is just any field, and we can bury it inside of some F of X modded out by a principal ideal generated by P of X, where P of X is, of course, it needs to be irreducible over F. So, is it clear when I write this containment relationship, what I'm talking about? It's a little bit of an abusive notation, because after all, this is a world of cosets, whereas the base field might not have those cosets. But if we even go back to the example we were just looking at right here, right, the elements of this field, this is a field with 343 elements. All of its elements, right, look like this form. But included in that would be literally just the constants. So those constant polynomials can be identified with F itself. So we can view, I mean, and even if you just look at this one, right, the 0 and the 1, if you just look at my whole entire table and just look at the first two columns only, I have 0 and 1 here. I can either do plus or multiplication, right? And I've just got this filled in. This is a little field that sits inside of this whole big picture, right? So we can actually view it as a subfield of the field of size 8 that we created by modding out by an irreducible polynomial. So a couple of nice ways to kind of create field extensions here. And so what we're going to do in a minute is we're going to view the larger field. So if I think of one field inside of a larger one, we're going to view that larger field not as a field, but rather as a vector space, with scalars coming from the smaller field inside of it. This is actually it's kind of a clever idea, but on the one hand, it seems kind of like a stupid thing to do, because you're gonna take a field where you have addition, subtraction, multiplication, and division, and you're suddenly gonna not allow yourself to do multiplication and division anymore. You're only gonna allow yourself to do addition and scalar multiplication, because those are the operations in a vector space. So it's kind of interesting that somehow by using less of the structure of the field, we can get more mileage in terms of understanding or progressing on this theme. So I actually find this to be kind of interesting. So what we're gonna do here for a moment, and this is in the book, it's kind of just the first section of chapter 11, is a quick little review on vector spaces. I will make this pretty quick. I know you guys have seen vector spaces a lot in your linear algebra classes, but just in terms of the definition, we can frame it using some of the terminology we have from this class. So here's the definition. I'm going to let F, of course, is going to be a field. Start with our field F right here, and then a vector space. Okay, so we're going to have a definition of something that's probably pretty familiar to you already, but I'm going to write the definition using the language that we've had from this course. A vector space V over F is an additive abelian group. So I don't know if any of you guys, do any of you recognize this book? Okay, you better say yes, okay? If you don't say yes now, you're in real trouble. In this book, we actually define a vector space using 10 axioms. It's like it takes an entire page to write it all out. I don't know if you realize it or not, but I've already expressed 6 of the 10 axioms in just what's up here so far. The fact that it's an additive abelian group means that there's a 0 vector. It means that there's additive inverses. It means that it's commutative, it's associative, right? It's got to be closed, right? All these axioms are already there. So the only axioms that are missing are the ones that involve the scalar multiplication. So there's 4 more axioms. So let's add that now to the definition. So with a scalar multiplication, right, such that I wonder what would happen if I asked my 250V students to write down the definition of a vector space. I've never put that on one of my exams. No good, Miguel? It would be probably asking too much. There's so many axioms, they would hate me. Anyway, so such that we got 4 axioms here. Let's get them written down. First of all, the distributive laws, right? So if I take A times the quantity V1 plus V2, that should be equal to AV1 plus AV2. This would be for all scalars A from the field F, and for all V1 and V2 from the vector space V. All right. So that's the first distributive law. We have to be able to distribute scalars across vectors, but we also have to be able to distribute vectors across scalars. So we would have another axiom that looks very similar. A1 plus A2 times V, right? This should be equal to A1 times V plus A2 times V. This would be for all A1 and A2 from the field, and for all vectors little v in capital V. So it has to be distributive in that manner. So those are the 2 distributive laws. The third scalar multiplication oriented axiom is just the associative law of scalars. So if I take A1 times the quantity A2 times V, this should be equal to the quantity of A1 times A2 times V. Okay,
And I will just use a ditto symbol over here. This would be for all scalars and vectors. And finally, the fourth axiom that we have to add on to our list, a very exciting axiom indeed, is that if we take the scalar 1 and we multiply it by v, we better get v back again. It seems odd that we have to require that. But I actually think in my book, if you look, there's an example of something I propose, addition and scalar multiplication on a weird set of vectors, and it turns out this is the axiom that fails. So you can actually make examples where that doesn't work if you're not careful. So these are the really 10 axioms of a vector space over a field. Yeah, Nikolai.
Is it, like, I guess the unit or of, F and V would be like an intersection between the two, or is it like, how does it work? There's similar elements.
So at the moment, the vector space V is objects completely independent from the field F. So I'm not even thinking that there is a 1 in the vector space V, because the vector space doesn't have to have, because there's no multiplication, you don't have to have a multiplicative identity element in a vector space. So at the moment, there can be no confusion here about what I'm talking about. In a little while, when we start putting one field inside of another field, we're going to view the bigger field as the vector space. It will have to have also a 1, which will be the same 1 that the base field has. You can't have two different multiplicative identity elements floating around at the same time. Yeah, that's basically because multiplicative identity elements are going to be unique. So whatever the multiplicative identity element is for the big, larger field has to be the same as the one for the smaller field as well. You can't have two different, yeah. Okay, let's write down a couple quick examples of this. Again, I'll try to go relatively quickly. Some of this is review. I don't mind. I guess I've timed this kind of well to do a review on the first day back from break. It's probably not a bad thing. So the first example would just literally be, these are examples of vector spaces. So we can take any field and build n tuples of entries from that field. So F to the n, by definition, this is literally a direct product of n copies of the field F. So you're just making slots out of these entries here. So that's certainly fine. And this is a vector space over the field capital F. So assuming we start with any field whatsoever, we can build a vector space that way. Okay, well, as soon as you think about doing direct products, you start thinking about, well, what other operations have we learned how to do this semester? Well, we can take a field and we can build matrices over them, right? So let's say n by n matrices over some field F, right? This is a vector space over F. Of course, matrices are not commutative under multiplication, but we don't have a multiplication of vectors, right? All we can do with vectors is add them and do scalar multiplication. So as long as I'm limited to that, this is a perfectly good vector space. In fact, they don't even have to be square size. I'm kind of suggesting here that these are n by n matrices, but they could be m by n matrices. It would still be a vector space over F. Not a problem. Third example is just building off of what we have on the board on the left here, which is that the complex numbers, which is sort of the biggest example from number 1 over there, is a vector space over Q of radical 2 and R. It's a vector space over anything that is inside of it. And again, why is that? Well, so how do I view this as a vector space? If it's a vector space, it has to have, well, an additive abelian group structure. Of course, we can, ignoring the Q and the R and so on, this is an additive abelian group. Okay, but on top of that, if we want to, we can use scalars from any of these smaller fields. And how does the scalar multiplication work? Well, it works just like how you would normally multiply in C, right? In fact, that's really the beauty of it. That's really the point that I'm going to now generalize here, which is that anytime you have one field inside of another, the bigger one can be viewed as a vector space over the smaller one. So if F is a subset of K, and these are fields, if you have one field inside of another, right, then K is a vector space over F. Yeah, K is a vector space over F in that case. Absolutely true. I like to draw the picture, you know, here's F, the base field, and then outside of F containing it is K. So you have this kind of a deal. And we're viewing K as the vector space in this example. So now I can kind of make the point I was making earlier a little more clearly. If I take, you know, obviously if I take two vectors in K, since that is a field, I can do addition and subtraction. And I can do scalar multiplication by some scalar down here in the field. And how do I do A times X? Well, I just multiply them as if it was in K, because K is a field, so that multiplication is already baked in, right, to how the field K works. So the weird part is we're not allowing ourselves to take X times Y. We're just not gonna do, even though we could do that, right? It would make sense to take, you know, two complex numbers and multiply them together. Yeah, we could do that, and we've probably all done it many times. But we're not allowing ourselves to do that when we're viewing C as a vector space, right? Because in a vector space, we don't do multiplication of vectors. We can do scalar multiplication. If this is a complex number and this is some real number, sure, I can view the complex numbers as a vector space over the real numbers and do a regular multiplication there. But we don't allow ourselves to actually multiply. So we're not, in other words, we're not taking full advantage of the algebraic operations in K. We're like somehow tying ourselves up a little bit. We're not giving ourselves quite so much freedom. And somehow that's supposed to be a good thing. That somehow this is how the theory of field extensions becomes interesting. And that we can actually study these relationships a little bit better. So, okay, the next thing in my list here, maybe we'll take a break before we do it. I want to talk about basis and dimension. Once we have vector spaces, of course, we have basis, we have dimension. And I will talk about that briefly, and then we'll move on to the next section. This is a quick little review, so we'll make it pretty quick. So let's take a 10-minute break though. Appreciate your patience with all this review stuff today, guys. But we'll get to some new stuff real soon. Take 10 minutes. All right, guys, maybe let's go ahead and pick things back up. I think everybody is back who is here right now. Yeah, I'm just gonna crank through just a few more pages of notes. I'm sorry if this is a little bit redundant of stuff you already know, but I think it's okay. We need to kind of ease back into it here as we move into April. So I'm just gonna talk a little bit about basis and dimension, nothing too heavy. But we will get to the meat very soon. So quick definition, nothing you haven't seen before. A basis feels weird because I taught this in 250B like a month ago. You guys are behind. A basis for V over F. Right, a basis for V over F is a set of vectors. Let's write the set as V1, comma, V2, and dot, 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 comma, Vn. That does two things. First of all, it has to span V. I won't remind you about what that means. That just means everything in V should be expressible as a linear combination of those vectors. And secondly, it needs to be linearly independent. So two requirements here.
It has to be a spanning set that is as cheap as possible. Linear independence to me means cheap. It doesn't cost us anything more than we absolutely have to have. So that's a basis for a vector space. And then, of course, right along with that, we define the dimension of the vector space. So the dimension of V over F. It's always important to reference what the base field is. Because you might have a series of extensions, one within another, within another, within another. You have to know, well, what is, maybe this is the complex numbers, but you're viewing it as a vector space over, could be anything, the real numbers, rational numbers, whatever, and the dimension might be different depending on what the base field is. So what is this going to refer to? Well, first of all, the notation. This can be written in two ways. One way is the dimension. I'm going to put a sub F of V. Or another notation, which is actually going to be more suggestive of what's going to be happening eventually in this class, which is to put V colon F. Have we seen that notation anywhere before? Yes, you have seen it before.
Oh.
This was when we had group theory and we had a subgroup of a group, we could talk about the index of the subgroup within the group. This notation is actually going to be relevant in the context of that notation. It's going to fuse itself together as we kind of come down the road here a little bit further. So those are the notations, and this is just the number of vectors, as you know. This is the number of vectors in a basis for V over F. Right. Okay, so maybe I'll write down a couple examples just to totally dot my I's and cross my T's here. We'll just look at some of these examples over here, maybe that might be good. Nothing too surprising with these examples, but just to get them into the notes here. So the dimension over F of F to the N. Anybody want to take a gander at that? From your linear algebra days. This is N, exactly. So that would be N. What about the dimension over F of the N by N matrices over F? How many basis vectors is it going to take to span the N by N matrices with coefficients over F? Isn't that? I don't think it's N. What if I had 2 by 2 matrices, right? How many basis vectors would it take to span that, where the A, B, C, and D are coming from the field, from the base field?
2, 4.
What was that? 4. Exactly, 4. The general formula here, guys, N squared. Okay. Anybody wants to stick around at 6 o'clock? I start going over some of that stuff in more detail in my other class. But anyway, I think that should be N squared, right?
That's only for square matrices.
Yes, yes. If these were M by N matrices, then this would just be M times N, right? So essentially I mean, we could actually give a basis for each of these. Maybe that's worth maybe helping over here. So the basis, right, for the first one, the basis that you normally would use would just the standard basis, so to speak, is where you literally just stagger the 1 into all the different entries here. So it's just a lot of zeros with a 1 that just moves into the different positions. And since there's N positions there, we get N basis vectors. In the case of matrices, the basis would be, the way I like to write it, you might have seen this notation before. These would be matrices, which are written as EIJ, where I and J are both between 1 and N. And what it is this is a matrix, this is an N by N matrix with AIJ equal to 0. I'm sorry, no, I don't want to say AIJ. With all zeros except 1 in the IJ entry. So there's one position in the matrix that's a one, and since the whole matrix has n squared positions, we can move that one into any one of those positions, so, yeah. Yeah, question.
Is this how you define it in your book, just out of curiosity, instead of the unique representation of a basis?
You mean using these E EIJs?
I meant for a basis itself. Like the way I had it is, yeah, it's a set of vectors.
Oh, this is a very standard definition. This would be the way you would almost always see it. It's definitely how it's in my book, but it's almost any book on linear algebra will define it that way. It is true that you could re-express it using a theorem to say that a basis is a set of vectors that spans every vector in V uniquely.
Yeah.
The uniqueness part sort of subs for the LI requirement here. So that is another way to say it, totally equivalent. Yeah, but I think this is pretty standard way to write it.
I had it the unique way in my 307, and I know Dr. Glesser did his that way too.
What book did you guys use?
Oh my God, what was that book?
Linear algebra done right?
That's what Dr. Glesser used. Dr. Glesser used Friedberg linear algebra, I think.
Friedberg, Insel, and Spence, that's the book I
Yeah.
used for 307. It defines it that way? That's very odd. I would not recommend defining it that way. This is definitely the standard way to define a basis.
I think it does. Yeah, I thought we started with.
The condition about unique representation, that is definitely easy to prove from these conditions, but I would not consider that the definition, but I guess it doesn't matter, right? A bunch of things that are equivalent, you can use any of them for your definition.
Right.
It may be a matter of personal preference, but I mean, I've been around a long time and I can tell you that this is by far the most standard definition of a basis. So, okay, and then let's just keep going with our examples here. What's the dimension of the complex numbers over the real numbers? Does anybody want to take a guess at that? Might have even done this one for you. Last class, I can't remember. So I want to write every complex number somehow as a linear combination of the basis. So if I wanted to, where the scalars are coming from the real numbers. Jason? Just two. Just two. That's very true. And so can you give me a basis that has two things in it?
One and I.
1 and I, exactly. See, every complex number has the form A plus BI, where A and B are real. And so that means that these two numbers will span all complex numbers. Every complex number can be written as a combination of these two. Now, if I want to do the dimension of the complex numbers over the rational numbers. So see, this is different. I've got the same set of vectors, but I'm only allowed to use scalars that are rational now. So it's a little bit of a different kind of problem. Anybody have a guess about what that would be? Really only one answer that would work. Jason? It's gotta be infinity. It's gotta be infinity. If it was not infinity, guys, then that would mean every complex number could be written as a linear combination of a finite number of terms, each of which has a scalar from the rational number set. You're gonna end up proving that the complex numbers are countable if you do that, right? Every complex number would then be a finite expression with scalars coming from a countable set. But the complex numbers are not countable. They are actually a superset of the real numbers, which are already not countable. So if you don't know that theory of countable versus uncountable sets, no need to worry about it. But there is no way to make a finite basis for the complex numbers over a cube. So basically, when you write infinity here, it just means that there is no finite list of vectors that we can write down.
And the nice way to write an infinite list then?
Is there a nice way to write the infinite list?
Yeah.
No, this would not even be a countable list of basis vectors. So when I write infinity, I don't just mean the small kind of infinity, which is sort of the size that Q is. I mean like the big, huge infinity So an uncountable set is one where you can't write the vector, you can't write the elements in a list. So you can't even make a list of these things, because if you could list them, well, then there's a first thing, a second thing, a third thing, a fourth thing, and it's now, basically back to the size of Q again. I'm going off topic here, but that basically if you take a countable union of countable sets, it's always countable. And if this was a countably infinite dimension, then you would actually be able to express C as a countable union of countable sets again, which it's not possible to do that. So I'm getting totally off topic. Like, I'm not expecting you guys to worry about that kind of topic so much here, but it's worth knowing.
You
Interesting.
basically need C as your basis then. It's kind of funny.
Yeah. Yeah, you really cannot get away with any kind of a finite set there. One more example, what about the dimension? So another example here, what about the dimension over any field of f of x? So we've already talked about building this extension field, so I'm gonna take f of x and mod out by p of x. P of x is irreducible. I'm gonna assume that it's irreducible over f. So we already talked about the fact that this will be a field in this case, and it will contain f as a subfield. So you're really looking at, this is f, this is k, and I'm looking for the dimension of k over f here. Does anybody have an idea what this formula will be? Write down, that's it. Yeah, well, let's write down the answer, then we'll talk about it. It's just the degree of p of x. It's whatever the degree of p of x is. Let me see if I can kind of explain that a little bit. So let me just give a quick little reason here. This is actually, it makes a lot of sense once you kind of think about it for a moment. If you write down your polynomial, let's write it down, p of x. Let's say that it equals a naught plus a1x plus ... plus a n minus 1 x to the n minus 1 plus, let's just assume that p of x is monic, so it just has a leading coefficient of 1 there. So we could write our polynomial. Well, I guess we don't need to do that. Let's just make it a generic polynomial. So a n x to the n, and I'm going to assume a sub n is not 0. So that it really does have degree n. Then the basis that I can actually use up here. Okay, I want to write down what is the basis. The basis is going to be 1 x, and I'm using brackets now to denote the elements in the quotient field. And then we would have x squared, and it would go ... all the way up to x to the power of n minus 1. That would be the basis. And you can obviously count how many things are here. There are n of them, n things here. That's where I'm getting the degree of the polynomial is n. So this is my basis of n things. Does it make sense? Like, I wouldn't put x to the n in this list. Why not? Because if I wrote x to the n here, then I would create a linear dependency, because x to the n can be rewritten in the bracket world, can be rewritten using the lower powers of x that are already in this basis. So if you throw any more powers of x into this set, you will lose linear independence, which is one of the 2 requirements of the basis. So I don't want to lose linear independence, so I leave that out, right? But these guys are definitely linearly independent. Come on. Imagine this is a homework problem or something, but if I took a linear combination, I mean, how do you test? Does anybody remember how to test linear independence? Okay. Let's just check. I would like to do this. I might be doing one of your homework problems for you, but that's okay. Because this is something students really struggle with, is this definition of linear independence. It's easy to do it from a computational perspective usually. You just throw the vectors into a matrix and do some calculation with it. But if you're trying to prove it more theoretically, it how do you check that these are linearly independent from a theoretical perspective? The way it works is you make an assumption that somehow these vectors cancel out in a linear combination. So C1 times the first vector plus C2 times the second vector plus C3 times the third vector, and so on, up until the Cn times the last vector, and you assume that it cancels out. Right? You make that assumption. And the claim that you have to verify is that all of the constants are then zero. Right, you then have to claim that, does this look familiar? This is the sort of the abstract definition of linear independence. If your vectors cancel out in a linear combination, the only way that could have happened is sort of the cheating way where you just put a zero, you must have put a zero in front of every term to begin with, right? That's what it really means. Well, how do we verify this? I just take this claim and I use the fact that the brackets respect scalar multiples and addition, and I put everything inside the brackets here, right? So I'm just going to do this. Everything inside of one set of brackets. You just manipulate it algebraically like so. But if this bracketed expression becomes zero in the quotient structure that we're working with, that literally just means that this polynomial, if it becomes zero in the quotient structure, it means it's in the ideal that you mod it out by. Anything that's zero after you mod out must have been in the ideal that you modded out by. Right? So that means that this guy is a multiple of P of X. So P of X would have to therefore divide this polynomial, C1 plus C2x plus C3x squared and ... up to Cn times x to the n minus 1. That we would conclude that P of X has to divide that. Anybody see anything wrong with that? Or, I mean, not really that anything's wrong, but here you have a polynomial of degree n minus 1. Go ahead.
Yeah, that's what I was gonna say, that it's P of X of higher degree than that one, so we can't divide it.
How can you take P of X, which is already of degree n, and multiply it by something and get a polynomial of lower degree? Actually, that can happen if you have zero divisors around. Because if you have zero divisors in your world that you're working in, then sure, some of these top coefficients could somehow turn into zero using those zero divisors. But we have no zero divisors, my friends. This is an integral domain, right? So you're not going to get anything like that happening. So this actually means by degree considerations, the only possible multiple of P of X that would make sense here would be if this thing was zero. So C1 plus C2x plus C3x squared and ... right? Up to Cn x to the n minus 1. That literally has to be zero. And I don't mean in bracket world zero. I mean literally zero as a polynomial. And if it's zero as a polynomial, then thus all of those constants do in fact have to be just zero. Yeah, so that's what you needed to prove. Okay. So these guys are linearly independent. They also span this quotient field because after all, everything in the quotient field can be written in the form of some linear combination of these guys. If you ever saw a power of x larger than n minus 1, you would just knock it back down, right? Using the fact that P of X can be reduced to zero. Yeah, so this, I've certainly explained most of the verification that this is actually a basis. Yeah. So the dimension is n, which is the degree of that polynomial. That's really what the point is here. Everybody feel okay with this? All right, well, that's, some good examples of basis and dimension here in the
more abstract framework of working over any field F, right? So for the most part, we're looking at some pretty abstract examples. Okay, if everybody's okay with that, I'm gonna just, I know I'm talking a long time today. On Wednesday, we'll do some group work and get you guys out of your chairs a little bit, but I just wanted to get this little review stuff done first. If we're all okay with that, I'm gonna start talking a little bit about the next section for just 10 minutes here. And it's a section called simple extensions. So this is 11.2 in the book. It's called simple extensions. And I'd like to just kind of get our feet wet with this. This turns out to be really, well, it's the most important, for our purposes, the most important kinds of field extensions that we can have. And it's a method for creating new fields out of old fields. That's really what it is. So how is this going to work? We're going to assume that F sits as a subset of K, and this is an extension of fields. So we have one field inside of a larger field. Okay, so nothing too bizarre there. I'll even draw over on the side. I might draw my picture again that I've been using a little bit. So I've got F inside of K. Now, so far, this is not a simple extension. This is just any extension, doesn't matter what it is. What we're going to do to make a simple extension is we are going to choose an element, and a lot of times the element will be called U, and U lives in K. So on my picture over here, I'm going to put U over here. It is actually okay. It's possible for U to be inside of F. That's allowed, but let's just draw it as if it was outside of K. And now I'm going to give you the notation. This is going to be the notation here for the simple extension of F, obtained by adjoining U. So we're going to write it as F of U, and the notation or the definition is that this is the smallest subfield of K containing all of capital F and the element little u. Okay. That is the, in words anyway, that is the definition of this. Well, by the very nature of it, it is a field. It is the smallest subfield of K. So what I'm doing here, guys, grab my other color here for a second. I'm building a field that contains all of F, and it contains U, and it has to be a field. So it's right here, this little shaded part in blue. This is the F of U extension that I'm describing right now. And this is called a simple extension of F. So this is a what's called simple extension of F. I'm going to say by U. It's a simple extension of F by U. Now, what we get when we perform that operation there will be a field by its very definition. But of course, it doesn't say that it will be an interesting field. So of course, I'm going to dispose of a couple of trivial examples here first. And then we'll have time, of course, next time as well to get into some more interesting examples of this. But I mean, the sort of the baby example of this would be if the element U that you chose already lived in the smaller field. Okay. Then if I take F of U, so I form this simple extension here, what is it going to be? If U is already in the smaller field F, then what is the smallest field of K that contains F and U? Just F, right? So, you know, as I said, it is a field that doesn't necessarily give you anything interesting. By the way, the idea I think that you might want to have in mind when you're thinking about this concept of a simple extension, it's kind of like taking a span in the language of vector spaces, right? You're forming, when you take the span of a set of vectors, right? What do? You form, all possible linear combinations of a list of vectors, which gives you a subspace of some big universe that you're in. And it's really the smallest subspace that contains those vectors that you built that span out of, right? It's kind of what this is. F of u is the smallest field that you can make that contains this element u and contains F. Okay, and by the way, we can do multiple iterations of this. So if you're wondering, well, what if I wanted to adjoin two elements? I can definitely do that. I can just adjoin them sort of one at a time and view that as two consecutive simple extensions kind of back to back. So we'll definitely see some examples of that as well. But before I get too carried away here, let me write down another example. Let's suppose that F is the rational numbers. This one is a little bit more of a concrete example. K is going to be the real numbers, right? And let's take U to be the square root of 2. So this time I really am going to use an element that is not in F, radical 2, which is not rational. So then when I build the simple extension F of U, this becomes Q of radical 2, which is a field. We've already seen it before. It's literally expressions of the form A plus B radical 2, right? Such that A and B are in Q. So this forms a field that is inside of K. And it's really the smallest field that contains radical 2 and every rational number. So every rational number is represented here. Just take B to be 0, you get every rational number. And if I take A to be 0 and B to be 1, I get radical 2. So certainly it meets the condition of containing Q and radical 2, right? And why is it the smallest possible subfield of the real numbers that contains those things? Well, because of course the field has to be closed under addition. So I have to be able to take a rational number and add it to radical 2. And it also has to be closed under multiplication. So I have to be able to take multiples of radical 2, where those multiples could actually be from Q, right? So, and so then combining the addition and multiplication together, the closures of both of those operations actually forces all of these expressions to be in the set. You cannot make something smaller than that. But this actually is a field. I think we did this in the homework, right? We had to actually prove that, oh, everybody here has a multiplicative inverse that looks of the same form. And so it actually becomes a field as well. What else? Just another really easy example here. I could also take my base field to be the real numbers and my extension field to be the complex numbers. And this time I could, again, I'm just choosing a very easy example here, guys. I'll just let U equal I, right? So this time, I don't think anybody's going to be too blown away by this, because if I form the simple extension F of U, this is just R of I. And what is that going to be equal to? You know. Exactly. Anything of the form A plus BI, where A and B are real. So guys, here's another example where you get a field that's maybe not that interesting, right? Sure, this is definitely an extension of the real numbers, but the extension that you ended up with was actually the whole big K that you had started with in the first place. So examples 1 and 3 are sort of showing that when you form a simple extension, you might not get anything that's, particularly interesting out of it. But sometimes you can. So I need to find a way to tease you to come back again on Wednesday. Yes, question.
It feels like in that last example, if you chose anything that wasn't real.
Yeah, that's true. You could have chosen, so just choose U to be anything in C minus R, right? And you could build F of U and get the complex numbers. Totally true. Might be a little bit harder to describe the element. that you're getting as a combination of real numbers and u, but it would be very doable, yeah. Okay, so, we don't have a lot of really interesting examples up here yet, but of course, as I said, this can get more interesting if you allow yourself to do multiple iterations of these simple extensions. And in fact, sometimes these simple extensions are quite difficult to describe. So let me explain, like here, q of radical 2 was just a plus b times the square root of 2. But what if I adjoined something that's maybe not so nice, like cubed root of 2? Or the fifth root of 2? Or what about the fifth root of pi? Or some really bizarre real number, right? And like that. So you could, in that case, if I'm adjoining the fifth root of pi, I'm pretty sure that this is not the general notation of an element that's in q of fifth root of pi, right? Because I could actually take fifth root of pi times itself. That would be the fifth root of pi squared, which is not really in this form already, right? So this can actually become a relatively complicated simple extension. That's an oxymoron if there ever was one, right? But it can be something that's a little bit hard to describe. So the question is, can we always get a nice, I'm going to put that in quotes, a nice description of the simple extension f of u. And do I want to answer the question? The answer, I really should make you wait, but I get so excited. The answer is sometimes, and I'm going to say yes, as long as the element that you adjoined has a particular property. So if I adjoin pi to the rational numbers, I'm not going to get as nice of a simple extension as if I adjoin radical 2. As long as u is what's called algebraic over f. U has to be something called algebraic over f. Has anybody seen this concept? Maybe not in 302, or was it 350? Oh, in 350. Yeah. Interesting. Okay, so they talked about a little bit of 350. So let me write down the definition of this and then we'll quit after that. I promise I'll stop. It's very hard for me to do, but I'll try. So my definition here is that an element U that lives in the big field K, right, is called algebraic over F. It is called algebraic over F if it is a root of a non-zero polynomial. I'm going to write the polynomial as little f of x, which has to belong to capital F of x. So it is actually, the thing that's important here is that the coefficients of this polynomial do have to live in the base field. So for example, I'll just write one example. Radical 2 is algebraic over Q. Even though radical 2 is itself not rational, it does arise as a root of a polynomial whose coefficients are rational. So my f here is Q. And, to verify that definition, to verify that the definition is true, I have to give you a witness. I have to give you an f of x. I have to give you an f of x whose coefficients are rational, for which radical 2 is a root.
Can somebody tell me what polynomial they have in mind for that? What's a polynomial that has radical 2 as a root?
X squared.
X squared minus 2. Beautiful. If I plug radical 2 in for x, I get 0. So it does work. Now, this would not be a legal witness. This would not be a legal witness because the coefficients are not in Q, right? If I wanted to prove that radical 2 was algebraic over R, then I'd be allowed to write this one down. But if I'm proving that it's algebraic over Q, then my coefficients are not allowed to be irrational. They have to be rational. Yeah.
Is witness like a terminology, or are you saying like behold?
Behold, I mean, this is my way of phrasing it. Yeah, it's not really anything formal. Witness is like proof. Well, what's the proof that this element is algebraic? Well, I gotta come up with a polynomial. Here it is. All right, guys, as usual, I got a little excited. I always do. I love doing this. How many more classes? I don't want to even think about that. But I just love this stuff too much. I'm gonna stop talking. Let you guys have a good rest of your day. I hope you enjoyed this little review of vector space theory, and we'll definitely do some more stuff on Wednesday, including some group work. I will see you then. Thank you, thank you.
Are we gonna go over why exactly like extending R to C is not existing? Is there a requirement
Yes,
there?
yeah, that we'll be able to totally make that precise.
Okay.
It's basically, yeah, there's no room to put any other interesting fields in between. And it's very easy to prove that.
Got a maximal field.
Kind of, yeah, I mean, it's kind of a joke, but it's kind of not. It's kind of what it comes down to. Thank you, Nikolai, so much. Appreciate it.
I'm still waiting for comment, but